so I've got a couple leftover things that I intended to mention the other day to mention, and then otherwise we'll be talking about data frames and reading data into R for this class. I'll try to end up so that you guys have enough time to go to get to colloquium, get a nice seat. So left over from last class, we talked about functions, creating our own functions. We also talked about just loading in functions from other places. So that would be from a package that somebody created. We had the example of the car package. We installed the car package last time, so I don't need to, if I want to use the car package in this brand new session, I don't need to install it again. All I need to do is type library car, and that will load in all the functions associated with the car package. Now, I happen to know that there's a function called logit that the car package provides. The logit, it's a transform of it will take numeric data as input and transform it into its log odds. So it expects data coming in to be from 0 to 1, a probability. It turns probabilities into log odds. So it computes the odds, and then it takes the log of that number. You guys don't need to know much about that for now. We actually will get into log odds as sort of a thing when we start dealing with modeling data and binomial data, that sort of thing. But for now, just know that logit is a function provided by the car package, and we can call it by first loading in the car package by calling the library function. Oh, I had suggested the other day that you probably want to put in quotes the name of the package that you want, and then that means the logit function is available. The log odds of 0.5 is 0. The log odds of 0.7 is 0.84, etc. Another way that you can refer to this function is a little bit more verbose. Car : logit. That will yield the same result. Why would you ever bother typing this car : stuff if this works without it? Because sometimes
do they use like the same language between potentially different libraries?
Well, yes. So there could be another library that has a logit function, and if you've loaded both packages in, say there's a function, say there's another library called cast, something like that, and say this package also has a logit function. Depending on what order you've put these entries at the top of your code, depending on the order you've actually run these, determines which package's logit function you get if you just refer to the logit function all by itself.
I'm guessing it's the most recent one. I'm sorry for
interrupting.
Yep.
No. So yeah, if we loaded up car and then cast this would be when we run this, it would run whatever the cast logit function is.
Got it.
So if you really want to be explicit about your functions, which I think is in general a good idea, put the car : or the package name : and then the function name. That actually helps you figure out what packages provided the functions in the first place. I find it somewhat annoying when I see somebody has put a whole bunch of libraries or packages at the top being loaded in, and then they just use the functions from those packages, but I don't know which package provided which function to go and look for help on that. Or yeah, so it doesn't hurt to put the package name : function name, and there are circumstances where it can hurt to not put it. So I will try to always put it myself when I'm giving you examples. Okay, so we've talked about, I'm going to introduce a couple more data types today. We've talked about numeric data. We've talked about logical data, so true, falses, character data, character strings. there's another type of thing called a factor. So I'm going to first create an object, we'll call it A. It's the numbers 1 through 10. And I'm going to create a new object B, which I'm going to, I think I'll put as.factor of A. So I'm going to run this little bit. And I'm going to look at my environment to see what these things are, what it shows them to be. So A, did I clarify the difference between ints and doubles the other day? So numeric data can either be an integer, so here I said 1 through 10, so it's actually given me just the integers 1 through 10. If I put in a different sequence in which one of the numbers had a decimal place to it, so I'll actually concatenate the integers 1 through 10 and then add in 2.5 at the end. So if I look at A, it's the integers 1 through 10, but also a 2.5 there. That 2.5 means that the whole list is no longer all integers, so they all get turned into what's called doubles. Notice in the printout, they all have a .0 next to them. And here in the summary, in the global environment summary table here, it says num for numeric. If I undo what I just did and put A back to just the integers and I put A, it no longer puts the .0. In general, it doesn't matter. You don't need to really care about the distinction between ints and doubles. Don't think any of the tools we use are going to differentiate. So it doesn't matter. Just if you see int sometimes and num sometimes, that's the distinction. All right, so back to factors. I'm going to make this bigger. So what we had here for the code, we had A is 1 through 10, B is the factorized version of A. So what has it done? Well, it's clearly got a label here. It says factor with 10 levels. And if I tell it to print B, it has the same printout for the actual numbers there, but it also then says levels 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what factor does, it's going to make a little bit more sense momentarily when we start dealing with data frames, but factor will look at a list of items and figure out if there's repetition in that list. And if there is repetition, it will create a level for each unique item that it finds. So if we had C1, 1, 1 through 10, it will see that there's 4 ones in a row and then 9, 10, or so 4 ones in a row and then 2, 3, 4, 5, 6, 7, 8, 9, 10. So when I run the factor again, it still sees that there's just 10 unique things in this list. Indeed, they don't actually even need to be in a row. I could have like the 1. So I've added some more numbers, but they're just repeats of the original numbers that were in there. And whoops, is there a... So it's still seeing that there's just 10 unique things in this list. So what a factor is our own internal representation of a list of items where there can be some repetition. And fundamentally, when we get into doing real data analysis, factors will typically be like the experimental manipulation, so control versus placebo, control versus experimental group, or drug versus placebo. Usually factors have like a small number of levels, although you can also like often will turn our participant ID into a factor, so it's sort of considering that person's... sometimes we give people numbers as their ID, but the person with the number 10 isn't 10 times more something than the person with the number 1. So we say, okay, even though it's a number 10 there, let's turn it into a factor so that it treats it as categorical. And there could be repetition of the categories. So that's the other thing that happens with factor is that it's notice that there's quotes around, at least up in the description up here, there's quotes around these numbers. Indeed, if I say b times 10, it's going to give me a warning message. It's going to give me all NAs as the result, and it's going to say multiplication is not meaningful to factors. So converting something to a factor makes it so that you can no longer do math on it, which if it were the case, for example, where it's subject numbers and you really don't want to be fooled into thinking that you can do math on the subject numbers, this properly makes it so that it gives you NAs and a little error message saying you shouldn't have done that. Question?
Are they treated as characters then?
Well, they're treated as factors. Yeah.
Okay,
so you can get out the character labels associated with these factor levels, and that's we'll encounter a scenario where we have labels, but then we want to get the labels out.
Okay.
There's a way. There's also, if you ever, we shouldn't encounter it, but with the new tools. But it used to be that the tools for reading in data would often turn things into factors that weren't actually factors that you wanted to be numbers. And in that case, you had to go through a bit of a process to convert from the factor to a character, and then from a character to a number. We won't encounter that, so I won't bother going through that.
Cool.
So factors are something we're going to encounter. Int versus the other type of thing that we'll encounter sometimes is an ordered factor. So if I have a equals, and I'll put some strings in here. So low, mid, high, mid, low, high. So just a sequence of character strings, but say this is 3 groups in my experiment and the level of exposure to some stimulus. So some people got low, some people got medium, some people got high. If I want to create a new thing called B, which is which reflects that low is less than medium, and medium is less than high, I'd use an ordered factor. So this, we actually have to tell it what the order is. So we're not just going to give it A, we're going to give it multiple things. So I'm going to create a new line to reflect that there's multiple arguments being passed this ordered factor function. And I'm going to actually look up the ordered factor function because, I actually think it's just ordered. Why isn't that searching? Okay. As ordered. You could just put factor and ordered, but just to be clear, I'll put it as as.ordered. Okay. As ordered doesn't take any arguments except for 1. So maybe I have to use ordered, because the ordered allows you to take the levels. So the argument that we didn't name up here, so we just passed it A. I could have said x equals A. So here, x is going to be equal to A again. But we want to give it the levels. And you just need to tell it what the sequence of levels are. So you're telling it expect a bunch of lows in there somewhere, expect a bunch of meds in there somewhere, and expect a bunch of highs in there somewhere. And the order in which you give it is the order that it's going to apply to this as an ordered factor. So if we now look at our environment, we now see that B is an ordered factor with 3 levels, and it shows the levels here with the sign indicating that they're ordered. Now what's interesting is that you can actually see there's enough room here for it to show all the levels, and then it actually shows 1, 1, 2, 3, 2, 1, 3. So it's actually showing you like the rank of the, so this is the first. So that's actually kind of what factors are doing behind the scenes. They associate labels with each entry, but also a number with each entry, indicating the rank of that number. It's not something that you need to worry about too much right now. Sometimes you'll see ordered factors, and not the way we do things, but or not the way we will do things, but some other ways of doing stats in R will expect you to set up the factors as ordered in a proper way for you to do, say, like ordered categorical data analysis or something like that. We'll be doing that kind of a little bit more manually than the other packages, so we won't need to care too much. I just wanted to expose you to the idea that there's factors and ordered factors. There's other data types that you can encounter. So there's actual data types that encode dates and like times. We won't be dealing with those so much. There's other ones that actually deal with time series. And really what a time series is just a value plus an associated time with it. There's a special type of data object that can make that pairwise association across multiple observations. Really, it's kind of like a data frame, but that we'll talk about in a moment, but they give it a different name. So I just mentioned data frames. Data frames are what you'll mostly be dealing with. Everything we've been doing so far in terms of creating an object that has maybe a single value or maybe it's a vector with multiple values, that's actually rarely what you'll be dealing with. More commonly, you'll be dealing with data frames. You can think of a data frame as an Excel spreadsheet. It's something with rows and columns, with the limitation that each column needs to be the same kind of data. So you can have a column of characters, you can have a column of numbers, but you can't have a column that's both characters and numbers. So that's actually how most of us collect our data. We usually have nice sort of tabular data. So we'll get into reading in data, but just to give you a feel for what I mean by these data frames, there's actually a bunch of data frames built in that you can access. Just like we had the print function was built in and we could access it right away. There was another thing that was built in that we didn't the other day that I mentioned. Was it a data set? Oh, letters. So letters is there. We can refer to it. There's actually data sets that are available. So cars is, you should be able to just run that, and it gives this big printout. So you can see that it's got a sort of like tabular format in that it's got a header here. There's 2 clear columns and multiple rows. This like blank space, this column here actually is just the row numbers. This column would be the speed information. This column would be the dist information. So for a data frame, you can view it just by, as we've been seeing with all the other objects, just putting the object name and hitting enter. You can, of course, do the same thing, which is print and hit enter. A better way to view it, though, is capital V, i.e. W. And that will bring up a little spreadsheet-like viewer up here, and you can just scroll through it as you like. This is a smallish data frame in that it only has a couple of columns and 50 rows. If you had more than like a couple hundred rows, then it would truncate the printout when you tried to print it. So, but if you do the view version, it would all come up here, and you can scroll up and down through it.
How did you get that tab with all the data to appear?
Capital V-I-E-W,
okay.
view. So,
I have a question.
Yeah.
How do you go back now? I have it set up a little bit differently.
yeah, now you can just click on that tab back to go back to your code.
That one?
Yep.
Thanks. Oh,
Yep,
cool.
there we
Thank
go.
you.
All right, so yeah, so I suggest never try to look at a data frame right in the, never print out a data frame, always view the data frame. There's some tricks when you're dealing with the data frame to see, well, you can view the whole thing like this, but there's some summary views you can do. So str will work on any object. So for example, we still have B defined up there. So if I look at this str of B, it's really showing me the same thing that's up here. Str of cars will give me a little summary of what's in the cars data frame. So it says there's 50 observations of 2 variables. There's a speed column and a dist column. And it tells you, so these dollar signs are a very standard way to refer to a column within a data frame. We'll use them explicitly in a little bit, but for now, that's what this dollar sign is saying. It's saying, okay, there's a column called speed, it's numeric, and it shows the first few values. There's a column called dist, it's numeric, and this shows the first few values. So that's str. Another way to get a quick little summary is the summary function. And that will go through each column and compute a summary of sorts. Now, this cars data set just has 2 columns, so we're going to get 2 little tables of summaries. And those 2 columns are both numeric. So summary, when it encounters a numeric column, it gives you the mean, the min and the max, and first, second, and third quartiles, sorry. So that can give you a sense as to what's going on. Probably better to visualize, but we'll get into that in a little bit. So a couple more ways to just get a quick view of the of a data set. Head cars will just show the first little bit. I don't know why you would choose to do that over just saying view cars and seeing the bit there. Similarly, tail cars will show the, tail will show the last few rows.
How does it, what is it a
6.
certain percentage? Or?
6 rows.
Oh,
It
it's
shows
just
you the
all
first
these.
6
Okay,
rows, yeah.
cool.
So cars is one data set that's built in that just has those 2 numeric columns. Let's grab one that has some factor columns. Let's see. The sleep data set. It's another one. It's another smallish one. It's got 3 columns. 1 numeric column. The other 2 columns look numeric, but if we look at the structure, we see that there's the extra column is numeric, the group column is a factor with 2 levels, and the ID column is a factor with 10 levels. So this data set has been already turned into a factor for those 2 things. So 1 and 2 must be codes for a control group versus a treatment group, for example. So that's what it would look like if we did the structure on a data set with some factor columns. What does a summary look like? I'm going to resize this so that it prints okay. So again, with the numeric column, it's just given us a numeric summary. With the columns that aren't numbers but are factors, it will give you a count of how many rows are associated with each factor level. So there's 10 rows that have a 1 in the group column, and there's 10 rows that have a 2 in the group column. If it's got a factor that has more than 6 levels associated with it, it's just going to show you that same summary, but for just the first 6. If you want to get that same sort of summary where it's just counting the number of rows associated with each level in that that variable, you can use the table function. But to use the table function, you need to refer to a specific column within sleep. So what did I say was the way to refer to a column within a data set? Well, we can view the whole thing, but I just want to look at a table, or I just want to refer to a column within the sleep data set. $sign. So happily, as I type sleep and if I hit $sign, the GUI gives me the names of the columns that are in the object it knows about as being a data set called sleep. So I can say, give me a table of what's in the ID column of the sleep data set. That will print out. The first row here is all the ID numbers, and the second row is the count. You can actually look at like the counts as a function of multiple variables. So you just add sleep $group, for example. And this shows that there's, for each person, I guess, they were in both groups. So group may be a misnomer here. Maybe this is a within subject design, and it's just that the same person participated in both treatment levels. Alternatively, they misnamed the ID column and maybe should have said group 1, 1, group 2, 1. Usually, in all the tools we're going to use, it expects that across groups, you don't have repeated ID numbers. Like if there truly are different people, they shouldn't have the same ID number. Maybe they broke that rule in this. Yeah. Okay, so let me go back to here. So data frames are how people have organized data in R for a long time, but it can get pretty cumbersome when you start getting into very large data sets. So for example, let me see. Let's load in the tidyverse package. If you haven't installed it, you'll want to install .packages tidyverse. And that should go pretty quickly. So tidyverse is a meta package where when you load tidyverse, it automatically loads a bunch of other packages. So you'll see the message saying it's loading a bunch of things. I'm getting a conflict here because there's a couple packages that have that scenario where they have two packages have the same name for a function. So there's a function called filter in the dplyr package. There's also a function called filter in the stats package, which the stats package I think would have been loaded by car when I loaded up car. So this is a definite scenario where if you wanted to use the filter package, you definitely want to use that double colon if you wanted to use, the filter function from the dplyr package, and be specific about that. So tidyverse has loaded up a bunch of packages. Those packages provide different functions.
Question about the conflicts. So, do they do the same thing in the same?
Probably not.
Okay.
No. Yep. So those packages could be doing, so filter in the stats package could be doing something completely different.
Okay.
They just share a name.
Got it.
And so it's giving us a heads up that you probably, regardless of which one you want, you probably want to use the double colons to refer to it if you ever refer to it in this script. So tidyverse has loaded up a bunch of packages. Some of these packages come with their own data sets that they come. Is flights. I'm just going to go look it up. Hold on. R4DS. I think NYC. Oh, it's a whole library. Okay. So I think I already have NYC Flights 13 installed. Oh. And come on. Flights is in there. Okay. So this flights data set, I'm going to... So I just loaded up tidyverse. I also loaded up this other thing, NYC Flights 13. If you don't have it, you'll have to install .packages NYC Flights 13. We will actually use it more in depth in next classes, but this flights data set has, let's see. You can see the summary here. It's saying there's 336,000 rows, and there's a bunch of columns, and no matter what kind of summary I do, it's going to be, certainly it's going to be cumbersome to actually just type flights here and see the whole thing. Oh, except it didn't. This is because I had tidyverse already loaded, and I think NYC Flights was provided by somebody that's associated with the tidyverse. So what's going on here? I told you that flights was a data set. So it should be like a data frame. But instead of that trying to print out all 330,000 rows, it's just printed out 10 of the rows. And instead of trying to print out all of the lots of columns that are in this, it's actually not many, but certainly it wouldn't have been enough columns to fit on the screen. It's just printed out a subset of them. So this is what happens when you have a data set that's stored not as a data frame, but as a tibble. Now a tibble, I can't remember what the shorthand is for it. I think it's because they used to call it TBL, like the shorthand for it is TBL, like a table, but instead they decided to call it a tibble. A tibble has a lot of nice properties, one of which is that if you can actually literally view it a little bit, and it gives you some nice info, like, okay, these are all, this is an integer column, numeric column, numeric column, numeric column, and it won't try to spam your screen if you, by mistake, put it as the output to the screen. You can always turn data frames into tibbles using the as_tibble function. Now that as_tibble function is provided by the Tibble package, Tibble. So I'll put that at the beginning, as I'll try to remember to put the package name, : function name from now on. So if I want to turn the sleep data set into a tibble, I can just say as tibble. And it's taken the sleep data set. It can see that it's a really short data set, so it does show the whole thing when I want to view it. Maybe I'll store this as sleep tibble So we'll store that away in sleep tibble, and then I'll say, show me what sleep tibble is on the screen. And it shows me the whole thing. It's still maintained that this is a factor, this is a factor. Question?
What is DBL?
Double. That's, again, as differentiated from an int up here where there's no decimal places associated with any of the numbers.
Okay.
When it sees that any of the numbers have a decimal place, it gives all the numbers a decimal place.
Oh, okay.
Yeah.
Okay.
I mean, behind the scenes, R can store integers a little bit more efficiently than it can store doubles, so it will try to use integers wherever it can.
Why is it called a double? Is that a long
It's a big, it's a history of computing thing.
Never mind.
Yeah.
That's kind of why I was confused. I
Gotcha.
said how it was different, but I'm like,
Yeah.
what is
Yep. No, it's just a number with decimal places associated with it. So sometimes when you see other people working with data sets, they may be working with them as data frames. We'll mostly be working with tibbles, but there's no big difference between them. There's just some neat extra stuff with tibbles that make them a little bit nicer to work with. So we're going to now switch gears a little bit.
I'm sorry, I noticed because I have the environment tab, it stores sleep tibble as something different. How does it understand data versus value?
Okay, because it knows that a data frame is something that is
Special.
like, yeah, it's a, you can think of a data frame as a container that expects all the objects in it to have the same length. Each object can have its own data type. So this object could be a character string, this object could be a numeric vector, but they all have to be vectors of the same length.
Okay, so it has to be sort of pre-structured that way, and then when you store it, like with the sleep underscore tibble, it can recognize it as data.
Yeah.
Okay.
Yep. And in fact, if you create a copy of just sleep all by itself, so sleep copy equals sleep, it will show up there as well. So it's not just tibbles that show up. Any data frame will come up under data.
Yeah, that's kind of what I was wondering, if that was a consequence of the tibbler. Okay,
no.
Cool.
Yeah. Okay, so I'm going to close this script. So I've been somewhat bad in my use of RStudio so far. We've really been doing really trivial things. Haven't really been writing scripts that we'd want to save and rerun a different time. But I've got some data here that I want to use to demonstrate. Where'd it go? There we go. Demonstrates reading in data. So here's my operating system's file viewer. I've got 4 different data sets that I want to deal with. Let's start with the ant0 data set. So if I were a researcher and I had this data that I'd collected, in terms of like file management, I suggest that you have a folder named for the project that's associated with that, and another subfolder called data where you put all your data files. So there's a number of different kinds of data files in this, just for demonstration purposes. And when you come to a project, somebody's just sent you some data that you need to analyze. You want to open up RStudio. And so it's going to open up and point directly to your home directory, but you want it to be pointing to this directory. The way to do that and to make it so that every time in the future you come back to this project, it will start pointing to that same directory, is to create a project associated with that directory. So you can do it either by clicking File, New Project, or by clicking this little thing up here, New Project. Either way brings up the same dialog. So you can create a new directory. Well, we already have a directory, so let's use an existing directory. You can browse. Let's see. I will go to my Finder and pull this right there. That points to it. You could have searched out whatever. I could have gone through and found this directory by clicking in this thing here, but I decided to drag. In any event, this is the path to that directory. I've already just created a new session, so I don't need to open a new session, but it wouldn't hurt to do that. So I'm going to click Create Project. And what it's going to do, well, it actually looks like it's a create a new session anyway. Is that old session still there? No. All right, so we have the working directory has automatically been set to look at that ant0 directory. And we can also confirm that by looking here. Oh. For some reason, it pointed right into the data folder. Not sure why that happened. So I'll also show you that it's created this ant0.rproj file. This file is actually just a text file, but if I close RStudio and I come to this folder, I go away, have some lunch, come back, and I double-click that file, that will open up RStudio and will point it back at this directory. So that's how you should always, first of all, start off a project, put an tell RStudio to set up a new project, and it will put a .rproject file in that folder. And then whenever you need to come back and work on that project, you should do so by not opening up RStudio first, but by just going and finding that file and double-clicking it there. And that will open up RStudio in a new session and point to that location. So we've got this scenario where somebody sent me this data and I need to read it in. So it's in a folder here, data. There's a bunch of different ones here. That's because I wanted to illustrate different data reading scenarios. So the very first one I might want to read in is this one. Ant subnum, there's an underscore there you can't really see, 1.csv. I didn't intend this, but it happens that the .csv file format triggers the GUI here to make it clickable, such that if I click it, I get these two options, view file or import dataset. Let's just view file first. And I can resize this. CSV is a very common file format for text files where it's a spreadsheet, but the columns are separated by commas, comma-separated values. It's very common to have data in that format. The other kind, so you can kind of see that there's commas separating them. Indeed, if I go out in my own operating system's file viewer, Mac OS happens to have the feature such that if you do a little quick look on a CSV, it automatically interprets those as rows and columns. So that's a nice feature of CSVs. And another feature of CSVs is that they're so common that RStudio has built in, whenever you click on them, you get the option to either view them or import them. So that's what the view is. You just see what the contents are. But that doesn't help me because it's not, all it's done is it's opened up like a little text editor to view the file. It's not now available for me to do any computation on. You can confirm that by looking in the environment. There's no data frames or data sets in the environment. All we've done is we're looking at the data file. If we want to load the data file in for computation, we'll select the other option when we click it, the import dataset. So it will automatically load up the URL here or the file location there. And it will give you a preview of what it thinks it should import it as. Now this preview looks good. That's because I structured this file to be a very standard scenario where there's a header row and then comma separated and no missing data or anything like that. So if I were to scroll through this, it looks very regular in the way it's structured. Notice it's saying it's just showing me the first 50 entries. This file might be a lot longer than that, but it just gives me a preview for the first 50. You can tweak the way it's importing here. So for example, if we had a different file that were not comma separated, but semicolon separated, or tab separated, or just space separated, we could choose any of those options and it would tweak its import to do that. And it would do a dynamic or a live preview of what those new options would yield as a data frame. So there's a number of different options for tweaking how it reads things in. So for example, in the data set that I have here, the first row is the names of the columns. But maybe that's not the case. Maybe the first row is not the names of the columns, in which case you want it to put default names in there, x1 through the number of columns there are. In this case, that doesn't make sense because I actually do have a header row there. So you can tweak this until your data preview looks good. And that's actually what I suggest the first time you encounter like a data set is you use this little import text dialog to tweak the way it's reading things in to get it in right. But notice that there's actually down here also some code that it produces. Now, it's actually somewhat trivial code because I've accepted all the defaults, but it's loading the reader library and then it's running read_CSV. So I'm just going to copy this. I could say import, and it would then import that data set. I don't want to do that because I want to do things by code. So I use this import wizard to help me figure out what code I would need to read in the data. But once I get it looking nice, I then copy it and put it in a script so that I can run it anytime that I want. So I'm going to hit cancel and go out here. Now, in starting this project, I haven't created any files. Like, I haven't created a script yet. I just created this R project, so I would immediately open up a script. I'd also immediately save it so that if I have to go, I can save without having to rename. So my analysis, for example. So there's that.
Open up that one.
Okay. Sorry, Command-Shift-N. Alternatively, you can point and click, File, New File, RScript.
Okay.
Yeah, sorry. These keyboard shortcuts have become so ingrained. I do them without realizing I'm doing them. Question here?
If you had if you had done something other than the default settings during that file viewer, would the code be different? Okay.
Yeah. Yeah. So I can even. I think I'll need to change that for one of the next ones. So I'll show you how that is.
Okay.
So, having gone through that process of opening up the file, the import wizard, and just found what code would read my data set properly, I would paste that in here. Now, one thing that I don't like about the way that import wizard works is that, see this big long thing here? That is what's called a hard-coded path. It's not a relative path. It's somewhat relative in that it's saying my home directory, but it expects you to. So if I were to send this whole project to somebody else, they would have to create all these other folders that are higher up in the hierarchy, So better would be to have what's called a relative path. So I know that when this R project opens up, it's going to set the working directory to wherever this file is. And I also know that I'll structure things so that wherever this file is, there's going to be a folder named data, and that data folder contains all my things. So what I can do is simply delete all that other stuff, because I know that I'm in a folder that in turn has a folder named data. The slash means you kind of read these from the right. The thing on the right of the slash is the file, and the thing on the left of the slash is the folder that holds that file. So read.csv, we can load in reader. I'll also be explicit and say reader read.csv. I don't like those arrows, so maybe I'll replace that. Maybe instead of just loading reader, I'll load tidyverse. So reader is one of the things that tidyverse loads in. And I can run that. And we get a little bit of output from running it. So I've created a new object called dataset and put in it the result of running reader. It's printed out some output. And that output is just telling me what it's tried to guess as the contents of each of the columns that it found. So it's saying that I found 1, 2, 3, 4, 5, 6, 7 columns, and here's its guess for what each of the columns were. We could get that same information from that data preview that it showed us in the import wizard. So we can look at our environment, and we'll see that the data set is there. It's got all those columns. And if I say data set, it'll be a tibble. And we can see again the information about what kind of column each one is. Now, it says that there's 2 more variables, RT and error. So if I actually resize the screen, it'll show me those. So tibbles will update how many columns it shows you depending on how big your screen is. Question?
You had previously made that into a tibble. Yes.
Well, no, reader.
Oh, reader just.
Because reader is part of the tidyverse. It will always return tibbles.
Okay. Okay. Cool. Cool. Thank you.
Yeah. So that one was pretty easy. Reading in that data set. It's I haven't told you anything about what this data set is. I guess it's data from a number of subjects across a number of blocks, across a number of trials. And each trial can have sort of a level of these 2 variables, and there's a couple outcome variables. I'm not going to go into this as a data set unto itself, just as sort of this is an example of reading things in. So that one was pretty straightforward. For your own, as you are preparing data sets and producing experiments that create data sets, CSV is a very good format, same as tab delimited. I used to prefer tab delimited just because you can see them a little bit better, but now that I recognized that the viewer has the ability to, or the OS has the ability to have this nice table view. I like that. One thing that I've started to do is compressing all my data immediately. It turns out that, so do you know what I mean by compressing? You can do this either manually or have your experiment automatically compress them. So a benefit to compressing them, well, a downside is that I no longer can have that nice quick look on it. So there's 2 compressed versions, a zip and a tar.gsv or tar.gz. These are just 2 different compression versions. You'll notice a benefit is that it made it much smaller. So most of our data sets have a lot of redundancy in them. There's like a big column of 1s that it can see that redundancy, and be able to store the data more efficiently. So you'll get actually your data sets not storing up as much, taking up as much space on your hard drive. Now, admittedly, our data sets also aren't very big in the first place, so they're not going to take as much space in the first place. They'll read faster if you have them as compressed, because it's less time to seek off the disk than it is to compress or decompress. And a benefit that may be a little counterintuitive is that you can't edit them once they're compressed. So I suggest that you always keep your raw data as untouched as possible. That way, and in fact, make it so that it's hard to mess with your raw data once you've collected it. So putting it in a compressed format makes it so that you actually have to like double click to uncompress and then delete the compressed version, etc. So it's a good idea to make them untouchable so that any like manipulation of the data set has to happen in your code. And happily, where'd my sides thing go? I think if I click this, what will happen? Oh, no. So I can't access the import wizard by clicking them, just like I did with the import with the CSV, but I can just fire up the import wizard. So import dataset under file. And you can click any of these really, well, I guess do from CSV. And this is going to work even though our file is not .csv, it's a .zip or a .gz. So we look for the file now this time instead of it automatically being there. So we say in the data folder, and maybe I'll try this, this one. Yeah. So, yay, it actually still was able to read it in even though it's a compressed version. So it's still going to work. It actually messed up the first column name. Somehow the file name got put in that position for the first column name. Turns out that the zip version doesn't have that problem. The column name is maintained. I don't know why that happened. But you'll notice the file to read it in is just the exact same as before. So that's kind of just a little side note for your own data practices. It's a good idea to compress them. Oh, the final reason why I suggest it's a good idea to compress your data files is for data recovery. I had a scenario recently where a hard drive where we stored a bunch of the backup for our data went down. And it turns out that while compressed files like zips are very easily retrievable, let me back up and say sometimes when a hard disk stops like being readable, you can use software to retrieve data from that. Sometimes what's actually happened is that the sector of the hard drive that stores where files are stored gets lost, but the files are all stored just fine. So you have to have a piece of software go through and just look for patterns that are file-like in the ones and zeros that are distributed across the disk. And that can actually work very well for a number of different file types, including compressed files like zip and gzip, but not raw text files like CSV and .txt. Those raw text files, CSV and TXT, aren't distinguished enough in like their bit stream. So that's another reason, because I've encountered the scenario of data loss because I wasn't compressing. So they're faster, they're tamper-proof, they're smaller, and they're recoverable. So that's why I suggest you always compress your data after collecting it. Okay, so this is a scenario where I have just a single data file for, actually, this is a single data file for a single person. stored, but for that whole person, it's all stored in one data file. What if I had the scenario, which is these two files, where if I go, actually, I'm just going to go out in my viewer here. Half the data for this person is stored in one file, so this might be the stimuli that the person received, and the other half is what the person did. So you still have sort of a common set of columns in the two. They both have the subnum, block, and trial across the two, but one of them has Q and flank, and the other one has RT and error. And ideally, we want to just combine those two data sets. So how would we do that? All right, I'm going to make this bigger. I feel like the font size got bigger since the last class. So I'm going to create a data set called A. And it's going to be in the data folder, and it's the half a.csv. And I structured these such that I know that the default options to read CSV are going to work. And I can confirm that by saying view A, and it looks like that little preview that I showed you in the operating system. So lots of rows, but 5 columns. Ditto, I can do the same thing for B. And there's B. So again, we've now loaded B and A into R, and now we need to combine them. I'm going to pull up the help for data wrangling cheat sheet, which I highly suggest you keep on hand and or print out, laminate. And I have to resize this window. Combining data sets is the section we want. And there's different ways to join these two data sets. Usually what you want to do is a full join. This visually shows you sort of what the different ones happen. So if you notice, this data set A has for x1 entries A, B, and C, and this data set B for x1 has A, B, and D. So x1, there's commonalities between the two things, but there's also some missingness. So in A, there's no D, and in B, there's no C. X2 is a completely foreign column with regards to B, and X3 is a completely foreign column with regards to A. So if you made it a left join, that would make it so that the one that you put first, the one on the left, will get preferentially taken, and it's going to ignore the row that's completely unique to B. Ditto right join, it ignores the C row because there's no C entry in X1 for B. Inner join only keeps those rows that are actually common across the two, so you get rid of both C and D. And full join would join them both but give NAs where there's missing data.
What's with the by X1?
So
the reason I ask is because in both of them you have like X1, but in the lower ones there's only one X1.
Yes. So what you're doing is you're saying, I kind of want a new so X1 is a column that is like the common list of identities. So A in entry capital A in this data set is the same person, for example, as A in this data set. So you want a new table that has X1, X2, X3, and has 1 in the X2 for this person A, and T in the X3 for the person A.
But I mean, in terms of why doesn't it do, for example, when you do the join, why isn't it X1, X2, X1, X3? Is it assuming X1 is common because it has the same name and therefore it's merged
Yes.
together?
Yep.
Okay.
Yeah. So this by, you're telling it what is the column that contains the information that's common across the two.
Okay. Having said this, and I apologize if this is a little bit too far, what if you happen to have an error in, like, say, for example, you're manually typing out, trials or whatever,
Mm-hmm.
and your data, and for one of them you have, one column that's trials, and in both of them you have trials,
Mm-hmm.
But you make an error in entering the trial number in, one of the columns in one data sheet or the other data sheet. Will it still import both of those and just overlay them?
So are you saying like one data set you have trial and the other data set you mistyped and it says trail?
Yeah.
You can fix that within these two things, but you would need to do it explicitly.
Okay. And now what if you have, for example, trial 110 in data set A and then trial 129 in data set B, and you just happen to miss the last one. The last one says 11 or whatever. Would that just randomly add it?
Well, that's what differentiates these different types of joins.
Okay.
So the left join, if B is the one that's missing like an entry, the left join would create a scenario where there's an NA just in the column for B that is missing data for that.
Okay.
This is why I actually suggest you always use the full join, is because it will highlight when there is missing data. If you suddenly have NAs in a column that didn't have NAs before, it will allow you to see where some errors might have happened. I haven't really told you about NAs in the first place. NA is a special thing in R. So if I say NA, it knows about that. If I do little NA, it doesn't know what that is. NA is like it's a code for a missing value, not something. So you can't do math with NAs. It just comes out as NA. If you try to do logic with NAs, it comes out as NA. So any operation against NA yields an NA. Ditto, you can't compare an NA to itself. So back to this example where we had these two data sets, A and B, but we knew that we just want to join together the last two columns in B with against the last two against A, for example. We just need to port those over. That's where dplyr full join comes in. So I'll create a new thing called, D is dplyr full join, and A, B, by equals. And you can just have a single column that specifies like what's common, but these ones have 3 columns that are common. So say sub, whoops. So I'm going to put these on different lines so that we can see them more easily. A, B, by, and last one.
So now if you, for example, put by C subnum, and then don't put block and trial, it would do subnum as a common, and then it would put in block and trial for both A.
I'm actually not sure what it'll do. Let's check. So I just want to confirm with you guys that this did what I'm proposing it did, which is to create an object that now if we say view D, should have just had like the last 2 columns of B concatenated onto the side of what A was. And it has indeed done that.
So it's something just as simple as that. Is there a benefit to doing it here rather than just copying and pasting it?
Oh yes, no,
Okay.
because copying and pasting would be first of all reproducible, and one thing that I found in moving to sort of the R way of doing things, because for years I was doing like spreadsheets and doing copying and pasting, is that errors when you are doing things by hand tend to be random. Errors when you're doing things by code is systematic. it's easier to see systematic errors than it is random errors. Systematic errors come out as like big blocks of something weird happening, whereas random errors are just like, oh, this number, a decimal place got moved over one for this just one entry versus the others. So, and even copying and pasting, I've encountered my own plethora of copy and paste screw-ups that I highly suggest that you, once you've collected some sort of representation of the raw data, do whatever you can to put any wrangling of that data into whatever compressed, like aggregated version or whatever you need to do it by code. That way there's a full record of what was done and there's not random errors, which are harder to catch.
So really quick question. In this case, when you did by equals C, sub-noun block, etc., you have to create the vector in order to be able to use it for more than one thing.
Yep.
But if you wanted to only sort it by one, you could simply say by equals.
Yeah, I could have just said.
Okay.
So let's actually see what happens when we do this. I don't know. D and view D. It has kept block and trial. So it has recognized that there's these other columns called block and trial in there. So A has the columns Q and flank as unique, and B has RT and error as unique. So it doesn't need to do with anything with those column names. It just puts Q and flank and RT and error wherever that is. There we go. But for the ones that are common, but we actually haven't told it that those are like merge by columns, it actually keeps them there and it just puts a .x. So these are the values that it found in the first one, A, and the .y is the ones that it found in the second one. I guess
Is it supposed to have different trials for X and different trials for Y?
Nope.
Because if you look at D, sorry, it's just you have trial.x and they're all one, and then trial.y.
Ah, yeah. So that actually has screwed up quite a bit. Yeah. All right. I thought it was being a little bit smarter than it actually is. Yeah, it's in like if you notice, this is a much larger data set than the original one was.
Oh, is it sorting by trial.x first? And
Yeah.
Is it sorting block.x and then trial.x and then block.y and then trial.y?
Yeah, I'm actually not sure what it's done. Certainly it's nothing smart. So if you have the information about what actually is repetitious between two data sets, put that in by. It's also fairly smart in the sense that you can not specify what's common, and it will figure it out.
Oh, so no.
Joining by, subnum block trial.
So wait, so if you specify one but don't specify others, it'll keep
It can,
all the unspecified ones discrete?
yeah.
If you
Yeah,
don't
I don't know.
specify anything, it figures it
Yeah.
out? Okay.
Yep.
I mean, I guess that makes a sort of sense.
Yeah. So, yeah.
This is where you have to be careful if you accidentally typed in made typing error.
Yeah, exactly.
And you may be about to do this, but is there a way to then save this as another CSV? Save the joined?
Oh yeah, if you wanted to. There's not a big reason to do that because you would just, coming back to this data set later, you just rerun the code that joins it all together.
Yeah.
Yeah. Okay, that's merging. Okay, so next up, it's rare that you just have like one data file, especially if you're following my suggestion that you compress the data file as soon as you get it from your data collection apparatus, which if we're in psychology, typically it's observing individuals, maybe individual people or individual rats or something like that many times. So oftentimes you don't have one data file, you have many data files. So next up is talking about that. So I'm going to close this project because the ant0 is not what I want to deal with anymore. I'm going to go to my next one, ant1. So I'm back with a fairly empty data or folder with just a data set. Here there's 20 separate txt files this time. These happen to be tab separated, so we'll have to figure out how to import those. But we also need to start up an RStudio project, so I'll open up RStudio. And I'll say new project and existing directory. And this time I'll click through and browse to it because I know it's in teaching there, today's date, and ant1. Okay, create project. So that will have created a file in that place so that I can always just, from now on, when I want to deal with this project, I can always just double click that to open up a new RStudio session pointing to that location. That's already been done here. So with these, I think they're not, so they don't, if I click it, it will not give me, I guess .csv is special. .txt doesn't give you the option to import it, so I will instead go File, Import Dataset from CSV, and I'll browse. So open up data, and I'll just grab any one. So the first one. Now I happen to know that these are tab delimited, so I'll change the delimiter to tab. Notice that that has changed the code down here. For some reason it's changed it to read.delim. There's actually a read, in the same way that there's a read CSV, there's a read TSV that has a default of expecting a tab. But otherwise, the first row is names, so that's good. So I'll just copy this code that it's given me for reading in that single file. Actually, it's given me some pretty overly verbose code. Read underscore TSV is actually going to do fine on this. So I'm going to say new file, rscript. I'll say save this as my ant1 analysis, library tidyverse. Load that in. And to read in that one file, file1 equals reader, read TSV is the one I want. File is data, what was the name of that file? It's subnum1. So I'm going to try reading this in. Did it work? Gives me a little preview of what it thinks each of the columns are. And I'll view it. And it looks like it read in decently. So this is one person with 288 entries. This is an experiment where we have people playing a really simple video game. Each trial is sort of like a couple seconds of the video game where they have to respond to something on screen. These two columns indicate like what was on screen while they were having to respond, and this is how fast they responded and whether they made an error or not. So these experiments, we usually like to observe a lot of observations per person and per combination of conditions that are of interest. So there's 288 observations from this person in this experiment. And presumably we have the same number of observations or similar sort of structure to the data set for each one of these people. So I want to read in everybody's data. Well, I could say file 1 is this person's data. And then I could say file 2 is this next person's data. Then I'd have to figure out, if I kept reading them in like that, I'd have to figure out how to combine them all. Happily, there's a function that will obviate the need for us to explicitly read in each file. Instead, we're going to give it the list of files it needs to read in, and then it's going to read them in using the function we supply. So the function we want to use, well, first actually, we should ask what files do we want to read in? We need to generate a list of all these files. We could do it by hand, start typing them in. So files equals C and sub, and I don't want to do that. That takes too long. There's a list.files function. List.files, if we take a look at its help, list.files has a number of different arguments. Path equals dot. That means by default it looks at the current place. That's what dot means, here. So we don't want to look here because what here is just the ant1 folder. We want to look inside the data folder. So we want to say path equals data. The other thing we want to do is list.files. Let's actually run that and see what's in this files thing. So I'll just say files. Print files. Sometimes I write print, sometimes I don't. So if you see here, we've got, it's saying there's 20 entries in this files object. You can look in their environment. We see that it's a vector of characters, 20 items long. Here's all the 20 items. If I want to be reading in each of these files, here's the example of using read TSV that worked. And here's the strings that point to each of the files. What's different about these two strings?
So data and the print files string.
Exactly. So list.files have given us the names of the files it has found in the data directory, but it hasn't appended the path. So if I were to try to immediately read any one of these files, I would need to somehow append that path myself, or change the working directory to that location. A better way of doing it is to use one of the arguments to list.files to have it add this data / at the beginning of each of these strings. And that's done by the full names. So by default, full names equals false. We're going to tell it full names equals true. So now if I run that and say print files, now each of the files has that data /. So now we have a list of files that sort of had the same structure as the original file that we read in and were able to successfully read in. We want to somehow tell R to kind of do a loop over this list of items, and for each item it encounters, run this function supplying that item as the value for the file argument to this function. So that's where the mapdf function comes into play. Now the mapdf function is available to us right away thanks to the fact that we loaded in tidyverse. It actually comes from the purr package, P-U-R-R-R. So I'll put that there. And mapdf is going to take a number of arguments, so I'll put some white space there. So the first argument is called .x, and it's the list of things we want to iterate over, the list of things we want to have as input. So that's the object that we created there. And it's got another argument called .f. And that's the function we want to run for each entry in this list. So what function? It's the reader TSV. We don't have to put like the parentheses or anything like that because we're just passing it the function.
Or per on line 14, do you need a second colon or no?
Yes. Colon, colon. Yep. So that will take in each of these files. It will run this as many times as there are files in this data set. So there's 20 file entries in the 20 character strings in this object called files. So it will run this command, read_tsv, 20 times. Each time it will grab a new one of the entries in the files list. So the first time it runs read TSV, it's going to grab the first entry in the files object and supply that as the first argument to read TSV. The first argument being the file that read TSV is supposed to read in. The second time as it runs through, it's going to grab the second element of the files list and supply that as the file argument for read.tsv. Now, I don't want to confuse you. Just because this object is named file isn't the reason why it's supplying each of the elements as the value for the file argument. We could have called this anything like Q. And it'll still work. It's that map_df will grab whatever is in the list that you're given as its input and supply that, the contents of that list as the first argument to whatever function you give it. Question?
How does this output it? Will it output it as like a giant table?
Well, and the final thing is that what it's going to do is indicated by the underscore here. It's going to yield a data frame. In fact, it's going to yield a tibble. So it's going to concatenate by rows. So
having said that, would you run into the issue with the fact that in files, your subject numbers are not in order? Like you have 1, 10, 11, 12 instead of 1, 2, 3? You your tibble in order of like 1, 10, 11, 12, and then all the way down to 2, and then 20, and then 3.
So it will read it in actually in the order that it's getting. So it will go 1, 10, 11, 12, etc. So in our final tibble, it will be out of order. If we cared about that, I will show you tools to reorder them.
Okay.
Most of the tools we, though, are using won't expect things to be ordered like that. So, yeah, it's an outcome that we can fix, but we don't need to fix.
Do the columns in every individual file have to be the same?
Yes, in the sense that if there's any new files, new columns in, say, the 10th subject has like a new column named Z, it will add Zs to every other subject when it's combining them together and put NAs for that column for every other subject. So whenever it encounters a new column, it puts NAs for everybody that is missing that column.
Now, in this case, you said earlier you don't want to copy paste by hand to do things like this. If you went into the Z column, can we remove the Z deliberately using the code?
Yeah. Afterwards, we can.
And now, I apologize if I'm jumping all over the place here, but say, for example, you had NAs, but the reason there's an NA was because there was no input and you want to mark that as a false or a 0.
Yep.
Is it possible to search in a particular column for NAs and replace them with a given?
Yeah, we'll get into that next day. Yeah, so for now, we're using mapdf to iterate over a list and apply a function to each item in that list. And really what's happening, we're getting, for each item in that list, that item is being supplied to read.tsv as the value for the first argument of read.tsv. So this is going to spit out a data frame, so we want to store it somewhere. So call it all. X is not, oh, because I haven't run this bit yet, because I changed it to Q and then I didn't rerun all this, so I'll run that. So it will have done a bunch of output because it's running read.tsv. Every time read.tsv is run, it gives us this little output. So it's running read.tsv 20 times. We'll have 20 of these. But because every file was structured the same as every other file, this is just the repeated message every time. And if we say view all, it's a giant table, 5,760 entries. There's person 1. Let's get past 288, and we should start seeing person 2. Oh, person 10. Yeah, so there's that ordering that we can fix later. We can double check that we'll use a table to ask how many trials did we get for each person. So subnum is indicating each people, so we say all subnum. We can see that each person got 288 data files read in. All right. Go ahead.
Question. So with the map df, the .f function, does it only work if you're applying it to the first argument in that Because there's multiple arguments to the TSV. So files is the first argument. It's going to automatically assume that that's the one you're talking about when you're applying that vector. But what if you wanted to change a column type or specify something?
So you can have the same. So if you wanted to have it so that every time it's read, the read TSV, let's go back to the help for read TSV. Oh, I didn't. Okay, so what are the options to read TSV? Call names equals true. So if you want to say, have it so that call names was equal to false for every one of the files, you could actually add that here. Okay. Because mapdf will, if you notice, it's got that little ... And so this ... gets passed in as named arguments to whatever this is. So that's why that works. So any named arguments that are constant across all the items in this list that you want to supply to read TSV, you can just supply as named arguments to mapdf. If you want read.tsv to behave differently for each file that it's reading in, I'd have to think a little bit more about that. That's fairly rare. I haven't ever encountered it, because usually, you're doing data collection and some mechanical process that yields similar data for each person that you're doing. So, I'm sure there's a way to solve it, possibly using walk. I haven't looked at that yet, though. So I have another example of reading in that's sort of a more complicated data set that I'm not going to do today because it takes too much time and you guys have colloquium to go to. So any questions?
I apologize if I missed this earlier, but is there any chance you could send us the end data?
Oh yeah, so you can play with this after. Yeah.
Well, when we look.
Yep.
videos.
Exactly.
Just so that we
Yeah.
can check to make sure we all get the same values. and
Sure.
stuff.
Yep. So what I'm actually going to do is I'm going to put up what's called a repository, a Github repository. You guys will actually eventually, well, I'm eventually going to show you how to do your own repositories. These are useful for when you're sharing code across many people, and the code can be changing. So many people working on the same project, but it could be changing dynamically through time. You don't want to be constantly emailing out the code every time somebody makes a change, and that's what Git, Git is the name of the system. It solves that basically. There's a little bit of learning curve to that, but it's a point and click thing. You don't need to know code for that part of things. So yeah, and I'll show you that later when we actually start working on projects. But I will set up a repository for the course that will just mean that it's constantly updated and you guys can just download as new data sets are added to it. Yeah. Alrighty, great. Save this.